Hi, in this video we'll go over an introduction to software engineering. Let's begin with the definition of engineering. What is engineering? So basically it is the systematic application of existing scientific knowledge in order to create and build effective solutions to some practical problem. So our goal here is to build a good solution, a cost-effective solution, and a quality solution. And the same definition, when extended to software engineering, basically we are trying to create a solution which is a software. So we're solving a practical problem by building a software. So the same thing, we want to apply existing software methodologies and processes in order to produce quality software. So software engineering can be viewed as a problem-solving activity. So basically what it involves is given a problem, understanding what is the nature of the problem by breaking it up into smaller pieces. So typically the problem-solving activity involves that analysis phase first, wherein we understand the problem better by breaking it down into pieces. And then the second phase involves a synthesis. So now that we've understood what those individual pieces are and how they can be built, putting those pieces back together to form our larger structure. So it is this process of conducting an analysis and synthesis. And in order to do this problem solving, we're basically using our existing techniques, existing methodologies and tools. Now, what does techniques mean? And techniques sometimes is also known as a method, but then I don't want to confuse you with methods from object-oriented programming, because in Java, method means something else. So we'll just call it technique. So basically a technique is a formal procedure for producing some kind of a result using well-defined notation. So a specific algorithm, a specific programming language, or a specific technique within a programming language, like inheritance. So those are our techniques. To draw parallel, like, if we're dealing with cooking, and a recipe from a cookbook is a technique, a recipe which shows step by step how a certain dish can be prepared. Same thing, a formal procedure or an algorithm in order to obtain a certain result is a technique. Methodologies, on the other hand, is basically a collection of techniques that can be applied across a certain kind of for certain kind of software development. So it's basically unifying it into a philosophical approach. So going back to the recipe example, putting together multiple recipes into a cookbook, that cookbook would be the methodologies. Again, drawing parallel with object-oriented programming, so we have techniques like inheritance, polymorphism. Now putting all of these techniques together into a unified approach, such as object-oriented programming methodology, so that's a methodology. It's a collection of techniques. And then finally we have tools, which are basically the instruments that will help us accomplish a certain technique. So in cooking, those tools would be our utensils and all the necessary things that you need in order to prepare the dish. In a similar manner, if it's object-oriented programming methodology, then our tools would be the corresponding, say, IDE in order to do the programming, the corresponding language, such as be it Java or C#. Those are our tools. And then say you use Eclipse in order to do the programming, those are our tools. And anything else that facilitates accomplishing our tasks of programming using object-oriented programming. So basically software engineering is this problem-solving activity that involves using existing scientific approaches, using existing techniques, methodologies and tools in order to produce high-quality software. So having said that, the goal here is, like I already mentioned, our software system produced must be of high quality. In addition to that, we also want to be able to build the system within a given budget and within the given time frame. And all of this must happen while change occurs. As you know, the software world is a fast changing world where requirements change pretty quickly, technologies change pretty quickly, there's new platforms, new technologies, and it's somehow very easy to change requirements. So our goal is to basically produce software while change is occurring, ensuring that it's high quality within the given budget and within the given time frame. And typically you'll see that software production has had a very poor track record. There are a number of examples in the history of software engineering, so starting with the space shuttle software, which has which is a huge software system. Its cost was $10 billion, and that was millions of dollars more than what was originally planned for. It took the amount of time it took to get built was 3 years late. It was 3 years beyond the originally planned time frame. Now, how about the quality? The first launch of Columbia had to be cancelled because of a synchronization problem with the shuttle's 5 onboard computers. And then when they looked into it deeper, the error was traced to some kind of a change that was made a couple of years ago by a programmer who changed the delay factor in an interrupt handler from 50 to 80 milliseconds. Now, the chances of this causing an error was small. It was very small, and it was not caught in the thousands of hours of testing, but then it occurred on the day of the launch, and the launch had to be cancelled or postponed. So that's the reality of the software world. Even with thousands of hours of testing, one cannot guarantee that a software system is bug-free. Even with the space shuttle software, till today, substantial errors still exist. Astronauts are supplied with a book of known software problems and how to deal with it. That's the reality. And there have been a number of other such examples in the history. And the reason for that is software development it's a complicated process. Understanding the application domain and coming up with a solution is complex. And simple things like, in this case, changing the delay factor in an interrupt handler from 50 to 80 milliseconds could cause such a big synchronization problem. Say for example, say you're sitting on a plane that's crossing the Pacific Ocean, and you press the call button to call for the flight attendant, maybe because you want a drink or something. The moment you press the button, say the flight takes a sharp left turn and starts diving into the ocean. That doesn't happen, right? But then it could happen because the kind of software systems that we have. So say there is a subsystem to handle all of these user interaction buttons that are there on the flight, and then there's your the actual flight simulator itself, and then these are multiple subsystems, and say there's a shared variable between these subsystems, and if that shared variable is made a global variable, then changing its value in one place could reset it for all of the other subsystems. And these kind of catastrophes could happen. So it's very important to choose, to design carefully, to even simple things like choosing our variables, the way we share the variables, and making choices of whether a variable should be a global variable or not. These have to be thought through very carefully to make sure that there's no big catastrophes happening with the software system. So having said that, so software systems are complex, and why are they so complex? Because the problem domain is difficult, and typically the team that's working on designing and creating the software system, they build expertise in the problem domain, but then they are working on multiple projects, and each problem is from a different domain, which means they have to, it's not just being an expert in software engineering. Now they need expertise in that application domain as well, and that's a hard, very hard skill to expect people to have. The development process is very difficult to manage. It's very hard to estimate how much time it would need to build a certain module, or how many defects is that module likely to have, and how much time will it take to fix them. So it is it's a very difficult process, and software tends to offer extreme flexibility. That's the nature of software, and that makes it complex as well. And with this flexibility comes change. So because it's flexible, then the requirements tend to change, and then the software team is expected to incorporate those requirements, those changed requirements. But that's not the case with the other engineering fields, not always. So say, for example, if a washing machine is being designed and built, the requirements for the washing machine are set forth at the beginning, and once the washing machine is designed and built, there is not much flexibility to make any changes in it. Say if you don't want the door of the washing machine in the front, you want it on the top, you want a top loading one. Once it's designed, it cannot be changed. But that's not the case with software. I mean, it is possible to change. Software does offer flexibility. Things could be changed even after it has been designed, but that adds to the complexity. How much change do we allow? And a number of times clients don't have the clarity of what they want up front, and the ideas evolve as we go through the process, and that's the reason for the continuous change. So software systems are complex, and then how do we deal with this complexity? So there's three, at a very high level, there's three ways in which we deal with this complexity in the software engineering world, and that's the goal of this video, is to introduce those three techniques. Now the first one is abstraction. So basically we want to at a very high level abstract out the key ideas of what is it that needs to be built. The second one is decomposition. So basically break up, divide and conquer. We want to break up this huge complex system into smaller pieces, because as humans, we're able to deal better with smaller problems. And then hierarchy, basically organizing the smaller pieces that we've obtained into some kind of a hierarchy. So abstraction, decomposition, and hierarchy are three ways in which we deal with this complexity. And we'll look at each of them in detail. So we'll start with abstraction. Our inherent human limitation is, it's hard to deal with complexity. So basically the way we deal with it is by chunking. We want to come up with smaller pieces and group them into collection of objects. So basically the idea is to do this chunking and then also ignore unessential details. So let's look at the most important details, the high level details first. And that's what we do with modeling. So we come up with models so that we can ignore some unessential details and focus on the high level important details. For that, we create what are called models, and we create different kinds of models in order to understand our problem space better. So the three different kinds of models are a system model, task model, and issues model. And I'll talk about each of these and what these mean. So a system model is basically, again, there's multiple kinds of system models. So the first one is an object model. So this is where you think of the system and its structure. What is the structure of the system? What are some of the different objects in it, and how are they related? So given any software system that needs to be built, now we're beginning to think at a high level, what is the structure? Again, essential. We're going to think of the essential details only. What is the structure of the system? What are the key objects in there, and how are they related and how are they interacting with each other, and that's what's called the object model. Another kind of system model is the functional model. So once you've thought in terms of the structure, then we want to think in terms of the functions of the system. What are the functions that it provides? And when we do object, we're just thinking about the structure. When we're dealing with the functional model, just think in terms of the functions, more from the user perspective. So what is the system supposed to be able to do, and how is the data flowing through the system between these different functions? So that's called a functional model. And then there's a third model called dynamic model. So how does the system react to any external events? And what is the event flow like? So here now we're thinking about the dynamic aspects of the system. How does it react to outside events? How does, when these events occur, how are they flowing? From which subsystem to other subsystem are they flowing? Are the objects in the system changing states as a result of these events? So those are the kind of things that we think about in a dynamic model. So in modeling, especially system model, we create all of these three kinds of models: the object model, functional model, and dynamic model. And depending on the kind of system, we may pay more focus on one or the other or all of them, depending on the kind of the system. And you'll get to see more of this as we go through the course. Task model, on the other hand, is all about handling the various tasks involved in designing and creating the software solution that we want to create. So in order to create a task model, again, there's multiple different kinds of models and charts. The first one is called PERT, Program Evaluation and Review Technique. It's called a PERT chart. Now the idea over here is to come up with a list of tasks that need to be performed for this particular software engineering problem solving activity, and then coming up with the dependencies between the tasks. What are the dependencies? So using a PERT chart, we can basically visually list all our tasks and the dependencies between those tasks. Once we've done that, the other thing that we're usually interested in is the schedule. How do we handle the schedule? Now, how can all of these tasks be accomplished within a given time limit? So that's handled through the schedule. So that's also part of the task model. And then third one is the org chart. So this is where we're dealing with the organization. What are the resources available to us, and what are the roles within this organization or a project? So which resource is playing what kind of role? So coming up with that org chart. So so like I said, as part of this abstraction, we begin to do modeling. We first do a system model to understand the structure, functionality, and dynamics of the system. Then we create what are called task models to better understand what are our tasks, how are we going to schedule them, and what's our org chart going to look like, who's responsible for what. And then the third one is an issues model. So there's going to be a number of issues that have to be discussed, brainstormed, and then resolved. There's likely going to be a debate over what are the pros and cons and what's the best way to finally handle it. So we have to come up with a resolution. Within the software engineering world, research has shown that it's always a good idea to document everything related to the issues and how they were resolved, and that's what's done through the issues model. So what are the open and closed issues? At any point of time, we want to have a clear picture. So the management wants to have a clear picture of what are open and what are some of the closed issues. What were the constraints that were posed by the client or the development team, and what kind of resolutions were made in order to resolve those constraints. And even we want to keep track of all of the closed issues as well, because at a later point, say some requirement changes and one of the issues comes back up. And then at that time, we want to be able to go back and look at the history of the closed issues and what was done and why a certain decision was made when the same issue arose, say a couple of years ago. So it's always a good idea to keep track of this the entire process. So to give you an example of how an issues model could look, so say for example, and this is just for explanation purposes, to use it as an example, say our issue is we need to determine what is the center of the universe. So the information that we have at hand is that Church, the scientist, said that Earth is the center of universe. And why did he say that? Because Aristotle said so. So we're basically documenting all of the our pros for why what is the center of the universe. Our first proposal is that Earth is the center of the universe, and then our reasons for why we think so. And then our second proposal is from Galileo, who says that the sun is the center of the universe, and says the reason for that is because Copernicus says so. And also there's a second reason, that Jupiter's moons rotate around Jupiter and not around Earth. So basically here what we're doing is we have two proposals and we have supporting arguments for each of those proposals. So using an issues model, we want to make sure we document all of these. So here's our issue. What's the center of the universe? Our first proposal, it's the Earth, and our reasons, our pros for it. And then in the year 1615, a resolution was based on the information we had at that point of time. A resolution was made that proposal 1 is the correct one, and we go with it. But later on, there was a new proposal, a second proposal, that earlier what was the resolution that was chosen is not right. The second proposal says that the sun is the center of the universe, and then we again have our supporting information for that. Our pro is that, so there's pros and cons for every proposal, and the purpose of this issue model is to keep track of all of those pros and cons, all of the arguments that were made. So we've recorded our pros, and then we go ahead with the arguments. The pro for proposal 1 is that we should stick with that because change will disturb people. But then the con is that we have some other additional evidence that Jupiter's moons rotate around Jupiter and not around Earth. So it doesn't make sense for proposal 1 to be correct, and so on. And then based on discussion of the team decides that the first resolution was incorrect, and they come up with a new resolution in 1998 where Church declares that proposal 1 was wrong, and they're going to go with the second proposal. So basically that's the idea of an issues model, where everything is tracked, all of the proposals, the pros, the cons, the arguments that were made, the resolution that was made, and the history of those resolutions. All of it is maintained for tracking purposes, and to go back to it when something similar happens again. Or if something needs to be changed, we want to go back and look at all the arguments that were made previously, so we haven't forgotten something. So that's the idea of issues modeling. And then you'll see that there's all of these models are close-knit and dependent on each other. So there's this interdependencies, and it can be shown in the form of this triangle with the system model at the top, which is mainly focusing on on the structure, the functionality, and the dynamic behavior of the system. And then we have the task model, where the focus is on the activities, the organization, and scheduling of those activities. And then we have the issues model, wherein there's proposals, there's arguments, and there's resolutions. So we need a way to keep track of them. And all of these three models are dependent on each other. And this is also known as the Bermuda Triangle of modeling. Now, to put things in perspective, and again to show you what kind of software engineering methodologies are used for this, for the system model, basically there's a language called UML that's used for modeling, which is a standard notation. So basically there's a way to create object models in UML using what are called class diagrams, and then for the functional model, there's what are called use case diagrams in UML, and then for the dynamic model, there's multiple kinds of diagrams. There's state charts, there's activity diagrams, and there's sequence diagrams. So all of these basically provide the notation, there's various different kinds of notation to represent these different models. And also there's a number of tools, there's tool support for it, and these tools automatically take these models and convert them into code. So an object model can be converted into template code. Of course, the code logic needs to be added to it, but then template code is produced by the tools. So this is basically our system modeling part of the triangle. There's again the object model. Whenever you create the model first and then the code, that's known as forward engineering. So we're creating a model and then creating code from it. In some cases, reverse engineering is done, especially when we're dealing with legacy code, and if legacy code needs to be enhanced, there is a situation where we start with code and then create our models from it, and then enhance the models and enhance our code. So that's called reverse engineering when we go backwards. So that's system models. Now coming to the task models, there's org chart, PERT charts, Gantt charts. Again, there's tools for creating all of these different kinds of charts that help with creating our task models. So Gantt chart basically helps in doing the scheduling. So it's basically a way to lay out your schedule for the different tasks and the different resources in the organization. And then we have the issues model that are modeled in terms of your proposals, arguments, pros and cons, the constraints, and then the final resolutions. And again, there's tool support to do that as well. So all of these together form the Bermuda Triangle of modeling, and by creating these models, the idea is that we are able to better understand the software system that needs to be designed and developed, and we better understand the needs of that software system, thereby dealing with the complexity by looking at the system at a very high level in an abstract manner first. So the idea is similar modeling is being done for a very long time now, and it's done in other fields as well. For example, if you look at fossil biologists, say they find a few bones or a few parts of the body somewhere, they're able to take that and build the remaining structure of the particular animal that probably doesn't even exist today, but then they're able to use the rules of anatomy to put it together. So that's how, so with little bits of pieces of information and existing scientific knowledge, they're able to create models of something that doesn't exist, or something that's huge, or something that's too complex, or something that's too small to see, but then can be visualized through a model that's created. So modeling is used in all of these cases where a system is too large, so it's hard to visualize, too small, so it's hard to visualize, it's too complex, it's hard to visualize, or doesn't even exist anymore, so how do we visualize it? So that's where modeling is very useful, and that's one good way to deal with software complexity. In the follow-on video, we'll look at the other two techniques of decomposition and hierarchy, and how they are used in dealing with software complexity. Okay, thank you.